Hey, Jeff Frick here, coming to you from Intel headquarters, R&B, the Robert Noyce building in Santa Clara, California. It's a full circle moment. It's where I started my career in tech way back in 1997. You know, we just had the Super Bowl just down the street a few days ago at Levi Stadium, and the hot Super Bowl ad of 1997 was the Intel bunny people. And they were folks dressed up in their clean suits, and they had all different colored clean suits, pink and blue and green and sparkly, and they built a whole ad campaign around the clean suits. And in fact, I think I bought some for Christmas back in 97. We'll have to go back and check the photos. It was a really hot item in the employee store back in the day. It makes a lot of sense here as we released the last of our 10 interviews that we did at Humanoid Summit, because we had Werner Kraus on. He's the head of robotics from Fraunhofer IPA, and he talked about standards and tests and really doing the things that's going to make it capable for robots to start to enter the world of clean room manufacturing. And I thought, well, you know, if they get into the clean room and they're clean, don't they stay clean if they don't have to leave and go home and eat dinner and see the family every night? And that's not in fact true. There's all types of contaminants that can come from the robot itself and cause a problem in a clean room environment. And those are some of the certifications. You talked about, you know, potentially stuff coming off the gear and with the grease. You talked about, you know, wear parts might have emit certain particles. He talked about cracks and crevices within the outer shape of the robot itself that might harbor, you know, a higher likelihood of dirt or things getting, you know, stuck or hidden in there. Even talked about, like, what is the surface? What are the surface materials and what are the attributes of those materials for the robots in clean room manufacturing? And the applications are wide. Obviously, manufacturing, which is why I'm standing here in front of Intel, is an obvious one. Another one is pharma, a growing opportunity for robots in clean room environments. And the third one, which I didn't think of right away, but you mentioned, is solar panels. So a lot of opportunities for robots to expand in more labor pools where there's a shortage of labor. As we've heard over and over and over again, standards, getting to standards, coming to standards, adapting to standards is really what enables the broad commercialization. And you got organizations like Fraunhofer that are doing the dirty work to sit down and actually define these things and write them down so that everybody knows what they should and shouldn't do. It's a great episode. I hope you've enjoyed all these episodes from Humanoid Summit. I certainly did. I learned a ton with every single one. I hope you did too. Thanks for watching. Thanks for listening on the podcast. We'll see you next time. Take care. Bye-bye. Fraunhofer IPA. Sounds like a beer.
Yes, yeah.
And you're from Germany. Do they have IPAs in Germany, or is that against the German?
Against the German law, exactly, yes.
I don't like IPA anyway. Hey, welcome back, everybody. Jeff Frick here, coming to you from the Computer History Museum in Mountain View, California for the second Humanoid Summit. It's actually the third one. They had one in the summertime in London, but this is the second one here in Mountain View. And it's amazing how fast the space is changing and the excitement in the air. I think it's tripled in the number of people, and they announced they're headed to Japan next summer. So a lot of exciting stuff happening in robotics. So many factors that are still being sorted out and worked out, and one of them is standards. And you gotta have standards because ultimately you're gonna have insurance, and you're gonna have business people buy up on this stuff. So you gotta have standards, and we're excited to have our next guest who's got 1,000 people working just on defining all the different types of standards that they might have to worry about. So welcoming in, he's Werner Kraus, head of robotics for Fraunhofer IPA. Werner, great to see you.
Thank you, Jeff, for having me.
Absolutely. So you said you have like 1,000 people just working on standards. It's a big problem. How are you organizing the the classifications of different standards?
Yes, we have around 1,000 people working at Fraunhofer IPA for production engineering and manufacturing. So we are implementing new solutions on the shop floor, and we are also creating the standards, for example, in the area of clean room AI certification, and also safety standards, where we are closely collaborating with the ISO and also making the investigations in our labs, basically.
Okay. So one of the things I learned last year at this conference was collisions. Basically, when a robot hits something, it's called a collision. And we don't want a robot knocking grandma down. We know humanoids are going to be in homes and out working with people versus an industrial robot that's behind the safety. So with collisions, you showed me some stuff before we got on. You don't only think about collisions in terms of the contact, but the angle of the contact, where it hits in the body, and you've got a whole different set of rules depending on even what part of the body before you get into the forces. Share a little bit about how you're sorting this and organizing it and how it's going to make humanoids ultimately safer to be near people.
Yeah, definitely. It is a big topic, as the ultimate goal of a human and a robot is working close together with us humans. And so we have a Unitree G1 and checked all kind of safety standards we know from the collaborative robot, but also from service robots. So for example, the robot has 30 gears and joints. It may also pinch people if you get in your finger. So there's also a question about the radius, for example. The locomotion one is quite well. So it also on uneven places, it does not fall. But we also made then also some collision tests, for example. So when the robot is moving down, it can easily reach 500 Newton of forces, and this is much too much when we compare it to the current ISO standard. And also, when the robot is colliding while moving, we also see that the collision forces are quite high, and that a robot which is only 135 meter high and 35 kilogram. So there needs also, as it clearly sees that we need some more safety methods in the humanoids.
So is the goal that those standards then will be implemented as a standards? For instance, you can certify that your robot, when it has a collision, will not have more than whatever the designated amount of force is, and then how is that implemented in all these different robotic form factors?
Yes, good question. On the one hand side, we are contributing these findings also to the current ISO working group on dynamically stable robot, where a colleague of mine is also contributing. They met 2 times this year already at Boston Dynamics and PAL Robotics in Barcelona. On the other hand side, we are consulting humanoid robot manufacturers, also how they can make their robot safe. For example, that they change the design, that it does not hurt so much anymore. But ultimately, I guess we need really some new kind of sensors which keep the distance between human and the robot, so that there's no collision appears at all.
Yeah. Now, you showed me before we got on some of the categories. One of the ones physical safety is an obvious one, but cleanliness.
Yeah.
So, what are you judging robots on cleanliness? What are the factors, and why is that important?
Yes, that's we need cleanliness when we are operating robots, for example, in clean rooms for chip production, when we are manufacturing solar panels, or also in the pharmaceutical industries. And just recently in China, Xpeng revealed a partnership with Bayer, the pharmaceutical company, on humanoids in the pharma industry. And there we have to check and ensure that the robot does not emit particles, because otherwise these particles from the grease or from wear would come into the pharmaceuticals, for example. And therefore we have around 30 to 40 tests, like can we clean the surface? Does the robot emit particles? Is it biological resistance? How does it behave with temperature, for example, to make sure that the robot can be safely and cleanly operated in a clean room?
Is the threshold of engineering standards way higher for something like that than something that doesn't have to be? I mean, when you told me that, I'm like, well, of course it's clean. It could be clean, and they could keep it in the clean room. It doesn't have to go out to see its family at the end of the day. But as you said, it's also emitting and creating its own problems where some of these issues can come. Is that much harder in the clean room environment than, say, our everyday things that we see over here in the expo hall? So would it be a really special purpose build?
Yes, definitely. Also, you have to really look into which vertical you want to go, and then also the surface and the covering of the robot will change. And so, for example, that the coating is not resolved, for example, so it will have a steel surface is one example. We also have to look into the edges. Are there any corners where some dust could be inside? As it's a story for its own, basically.
Right. Yeah. And is that a go, no-go decision on whether the robot passes for a clean room, or is there gradients of okay, or is it no, you cannot go in, or you can go in?
There are actually 9 ISO classes, also from 1 to 9.
Okay.
1 is the cleanest worldwide, and the first finding showed that there's something like ISO 5 would be the Unitree, which is a standard also in semiconductor industries, for example. And it's really a typical progress that we are checking the robot and giving then advice how to improve the design of the robot to reach a higher cleanliness class.
Yeah, interesting. Another bucket is energy efficiency. So why energy efficiency? That seems like that would be very highly variable depending on the form factor and the objective. So is it like energy density? What are you coming up with standards on energy?
Yeah. Also, the energy consumption is of high relevance when we are thinking of a operation in production, because it says, okay, by when I have to charge the battery or change or swap the battery. And we have found out that the Unitree has around 280 watts is the energy consumption, and this turns out to be something in a normal scenario that every 1 hour 40 you have to swap the battery. But also on the Summit we have seen some further developments, so high density batteries. So I guess 4 hours are partly already possible, maybe also 8 hours, a complete shift.
Right.
Yeah.
Yeah, I mean, because the battery is a whole different technology, right? It benefits from cars and everything else in terms of the energy density. Yeah. So what is the biggest surprise as you've been going through this on some of these standards that you didn't expect?
Actually, we also looked into one point regarding cybersecurity. There's also some rumors that the Unitree is sending data out, and we also could see that if you connect the G1 to the internet, it starts to send data to China. So it's giving live signals.
So it was true, not just a rumor.
Yes, indeed.
All right, Werner. Well, it's very exciting. It's just amazing on how many different levels you're defining all these different standards. It's very, very complex and very, very detailed to make sure that we get these things in a position where we can have them out and about with people.
Yes, exactly. Thank you, Jeff.
All right, thank you. He's Werner, I'm Jeff. You're watching Humanoid Summit. Thanks for watching. Catch you next time. Take care. Awesome. Thank you.
Thank you.